Question number 1. A block of ice of constant thickness floating on seawater with 1 centimeter appearing above the water level. If the density of ice and seawater 920 kg per cubic meter respectively, the total thickness of the ice block is. We know that immersed volume divided by total volume equals to density of solid object divided by density of liquid when immersing partially. When considering partially immersed object, immersed volume, we immersed total volume. I will consider it as Vt. We can get immersed volume divided by total volume equals to density of solid. I will consider it as d divided by rho. We can prove this equation by using upthrust, but it is MCQ, therefore we can use directly. Then immersed volume, we can substitute cross-sectional area into immersed height. Immersed height, simple H, divided by total volume, cross-sectional area into total height. Density of ice 920 divided by density of water 1000. Now we can cancel out cross-sectional area. Then we have given 1 centimeter appearing above the water level. This height is 1 centimeter. Then we can use, we have to find the total thickness. Total thickness means we have to find the H value. When finding H value, we can substitute simple H, capital H minus 1 centimeter divided by capital H equals 0.92. Then we can find the H value by using the equation H minus 1 equals 0.92 H. Then we can subject H minus 0.92, 0.08 H equals 1. Then H equals 1 divided by 0.08, 100 divided by 8, they have not given seawater, density of seawater. There is no density of seawater in the question. Then get the answer as 12.5. We can't get correct answer without using seawater. Then question number 2. A vessel containing a liquid of density ρ1 is placed on a weighting scale as shown in the figure, and a piece of metal of mass simple m and density ρ2 held by a string is immersed in the liquid without touching the side or bottom of the vessel. Now if the string is cut and the reading of the scale the reading of the scale will be. We have to consider the change of reading. We can't get correct reading because of they have not given the liquid volume or mass of liquid. Therefore, I will consider change of reading. We have to find the change of reading in second question. We can consider equilibrium of object, weight mg, it is given in the question, and there is an upthrust V rho g. V is the volume. We can consider ρ1, they have given ρ1 as the density of liquid G. Now for this object, density equals to mass divided by volume. I will use density rho 2 they have given in the question rho 2. Rho 2 equals mass divided by volume. Then we can subject volume, mass divided by rho 2. Now we have to substitute volume V. Then we can consider equilibrium. T plus V1, V rho 1 G equals mg. T plus, we can substitute V mass divided by rho 2. Rho 1 G equals mg. T equals mg minus m rho 1 over rho 2 G. Now we can get rho mg as a common factor. Tension is mg times 1 minus rho 1 over rho 2. Now we have to consider when the string is cut, tension should be 0. Tension should be 0. Therefore, upward force is decreasing by T, and therefore downward force on the system is increasing by T. Then there is an increasement of reading, scale reading. The increasement of reading should be equal to this value. Then answer should be 2 for the question number 2. It is the increasement of reading. Then question number 3. The diagram shows a mercury barometer. The point in the mercury column at which pressure is 500 mercury millimeter is A, B, C, D, E. There are 5 points. We have to find the point with pressure 50 mercury millimeter. Then considering pressure at E, this point should be 760 mercury millimeter, because of we know that pressure at this place should be equal to atmospheric pressure. It is open to the atmosphere. And when considering this point, it also 760 mercury millimeter. According to Pascal principle, the pressure at the same level in a same liquid is constant. Then they have given this height is 160 millimeters, and we know that when moving upward direction in a liquid, we can decrease the pressure. We have to consider point with 50 mercury millimeter pressure. Therefore, the corresponding point should be above this point, C, B or A. But they have given this end is a closed end, and this height reading is 920 millimeters. If we consider the difference is 200, 0 minus 0, 0, 12 minus 6, 6, 8 minus 6, 7, 1, 160. Therefore, there is a 160 difference when moving in upward direction to the point A. If we subtract 160, the answer is 600. Therefore, if there is a mercury column in this full part, we can't get the pressure at the maximum point is 500 mercury millimeter. But they have given a liquid level like this. Liquid level is B. Therefore, we can consider pressure at A should be less than 600, because of there is no a liquid in this part, and they have not given this height. I will consider if this height is 260 millimeters. Then pressure should be at 500 mercury millimeters. And there is a gas in this part. For a gas, we can consider that there is a constant pressure. Therefore, we can get the point should be C. 500 mercury millimeters pressure could be obtained at point C because of when considering this height difference 920 and 160 height difference. This height is given as 160 dB. We know that pressure is 760 mercury millimeters, but they have given 160 as the height value. Then we have to consider a point 500 millimeters in upward direction. 160 plus 500, 660. Then we have to move 660 millimeters in upward direction. Therefore, it should be C. We have to get the point. Then question number 4. A measuring cylinder contains 60 cubic centimeters of oil at 0 degrees. When a piece of ice was dropped into the cylinder, it sank completely in oil and oil level rose 90 cubic centimeters mark. When the ice is melted, the oil level came down to 87 cubic centimeter mark. The relative density of ice we can get according to Archimedes principle. Upthrust on ice equals to displaced water and displaced liquid weight. Upthrust equals to displaced liquid weight. They have given initial reading is 60 cubic centimeters. When piece of ice was dropped into the cylinder, new reading is 90 cubic centimeters. Therefore, displaced volume is 30 cubic centimeters. We can get 30 into 10 to the power minus 6 cubic meters. It is V. Volume. Displaced liquid volume. We can multiply by density of liquid, density of oil into G. It is the upthrust on ice. When ice is melted, new reading is 87 cubic centimeters. Water volume made by melting ice, 87 minus 50. Water volume, volume of water, 87 minus 60, final reading minus initial reading. Then 27 cubic centimeters. It is the water volume. Now we have to find the relative density of ice. We know that relative density of ice is density of ice divided by density of water. Density of ice divided by density of water. For the first situation, reading is 60. When ice cube is immersed in oil, reading is given as 90. When ice is melted, new reading is 87. we have to find the relative density of ice. Then considering this displaced water weight, we can get upthrust on ice. But when getting upthrust, we have to consider density of oil as rho, density of oil. And for both situations, mass of ice should be equals to mass of water. Then I will use mass of ice equals to mass of water. Mass of ice equals to mass of water. We can substitute mass of ice by using volume. This is the upthrust. Upthrust equals to displaced water, displaced liquid weight, and we know that ice volume is also equals to 30 cubic centimeters. Then mass of ice, 30 cubic centimeters, it is volume. I will convert it to cubic meters by multiplying by 10 to the power minus 6. This is ice volume. We have to multiply density of ice into then volume into density is the mass equals to, we can get water mass, volume of water 27 into 10 to the power minus 6, density of water rho W. Now we can get the ratio between rho I and rho W. Rho I means density of ice divided by density of water. It is the relative density. We can find the answer. Then we can cancel out 10 to the power minus 6, 27 over 30. Divide by 3, 10. Divide by 3, 9. 9 over 10, 0.9. Then answer is 3 for the question number 4. Then question number 5. A thin polythene bag containing 10 to the power 6 cubic meters of water with no air bubbles. Inside it tied by a light string and lowered into bath of water as shown in the figure. If density of water 10 to the power 3, the tension in the string is. If the mass of bag is negligible, there is no resultant upthrust on this object because of inner medium and outer medium are same, water. Therefore, we can consider upthrust on the water in bag is 0, upthrust 0, and in water medium there is no apparent weight on the object because of, we know that we can consider equilibrium Tmg, and outer medium also water. Then we know that displaced water volume, displaced volume of this outer medium is equal to the volume of bag, and when considering displaced volume, displaced liquid mass is equal to the upthrust. Therefore, we can get the upthrust on the water due to water equals to weight of the water because of displaced water volume, displaced water mass equals to mass of the object, same medium. Then we can get tension of the Code should be 0. Answer is 5 for the question number 5. Then question number 6. The given U-tube has both ends sealed and contains a liquid of density rho. The broad arm has twice the cross-sectional area of the narrow arm. If P1 and P2 pressure of trapped air, P1 is equal to, you have to find the P1. They have given a diagram like this. There is a difference between liquid height of two columns. We have to find the P1 pressure. Pressure at this place P1, pressure at this place P2. According to the Pascal principle, we know that pressure at this point equals to pressure at this point. Same level and same liquid. Then we can get pressure at this place P1 should be equal to pressure at this place P2 plus H rho g. Then we have to find the P1 value. It is the answer P2 plus H rho g. Answer 2 is correct for the question number 6. Then 7. An air bubble liberated from a bed of deep sea is moving upward. Which of the following graphs best represents the variation of the speed of the air bubble with time? We know that when moving an air bubble from seabed to sea level, pressure is decreasing. Pressure is decreasing. According to Boyle's law, we know that volume is increasing. When pressure is decreasing, volume is increasing. It is a simple theory. Therefore, we can get upthrust equals V rho g. Mass of air bubble is constant. There are two forces on air bubble, weight and upthrust. Weight is constant. Trapped air mass is constant for the whole motion. But upthrust is increasing because of the volume is increasing. Then upthrust is increasing. It means the upward force is increasing. Upward force is increasing. Therefore, object should be accelerate, and the acceleration should be increased with time. Therefore, velocity time graph should be like this. The resultant force in upward direction is increasing. Therefore, there is an increasement of acceleration. We know that acceleration is given by gradient of velocity time graph. Therefore, gradient should be like this. It should be increased with time. Then answer is 2 for the question number 7. Question number 8. A piece of cork is tied to bottom of container of water by light inextensible string as shown in the figure. When the container is moved horizontally to the left with constant acceleration, which of the following diagram best represent the changes observed at the water surface and the direction of the string? We have to remember that if the density of object is greater than density of medium, the object should move in backward direction when accelerating the system. You can consider an object hanging in a car. When car is accelerating, the object is moving to this direction. Same theory. For the water layer, when system is accelerating, moved horizontally, when the container is moved horizontally to left with constant acceleration, to left, we have to move to left with constant acceleration. When water, density of water is greater than outer medium is air. Therefore, water surface should be like this. It should move in backward direction. And the second theory is, if we are considering an object which has a lesser density than outer medium, when accelerating systems, this object should be moved in forward direction, like a helium balloon. Then, when considering piece of coke, it is like this in initial situation. Therefore, we can get that density of this piece of coke is less than outer medium. Now, outer medium is water relative to coke. Then it should be moved in forward direction like this. Then answer should be 5 for the question number 8. You have to compare density. Question number 9. In the diagram, AB is a thin uniform rod made of material of density rho, freely hinged at A to the wall of vessel containing a liquid of insensitivity sigma. When the equilibrium 1/5 of the rod projected outside the liquid, the ratio of density rho divided by sigma. In this question, sigma value also should be density, not sensitivity. Then we can consider the rod. When considering rod, there are two forces. A is hinge point. First force, weight, mg. It is weight of the rod. It is acting at the midpoint because of it is a uniform rod. Then distance is L over 2. Total length is L. Then upthrust. Upthrust is acting at the midpoint of immersed part. Length of immersed part they have given 1/5 of rod is projecting outside. Then 4/5 of the object should be immersed. Then this length should be half of 4/5. Half of immersed part. We can cancel out 2/5. Now we can get torque around point A. In considering torque around point A, the reaction there is no torque due to reaction at point A. Therefore, mg into you have to get, I will draw a diagram like this. mg, we have to get this length. If this angle is theta, we know that this is adjacent side. Hypotenuse is L over 2. Then we can write Adjacent divided by hypotenuse cos theta. Adjacent is x. X divided by L over 2 equals cos theta. Then we can subject x L over 2 cos theta. L over 2 cos theta. Weight into perpendicular height from A to the weight. It is clockwise torque. It should be equal to counterclockwise torque. Counterclockwise torque is upthrust into, when considering distance, we know that this length is, if the force is upthrust, this length is 2 over 5 of L. Now we can use same method, 2 over 5 L cos theta. We can cancel out L cos theta. Now we have to find the difference of density, ratio of density. Density of liquid is given as sigma. Then we can write upthrust volume, immersed volume. Immersed volume is 4 over 5 of total volume. Immersed volume. V rho density. We have to multiply by density of liquid. Density of liquid is given as rho G into 2 over 5. It should be equals to, we can write mass as density into volume, but when considering mass, we have to get density of object. Density of object is given as rho. Therefore, we can write V rho. When considering mass, we have to get total mass. This is the immersed mass, this is the total mass. Density into volume is mass. We have to multiply by G and we have to multiply by this half. Then we can cancel out G and G, V and V. We have to subject rho over sigma. 2 into 2, 4. Sorry, 4 into 2, 8. Multiply by 2 over 25. 8 into 2, 16 over 25. Answer is 1 for the question number 9. Then question number 10. Figure shows the cross-section of 3 hollow objects, 2 of which have openings closed with a soft rubber Rn, the other with an opening just floating openings closed with a soft rubber Rn, the other with an opening just floating inside 3 bottles of labeled ABC. When excess pressure is applied to the air above the water in all 3 bottles by pressing their mouth with hands, we have to consider the motion of the object. For first and second objects, there is a rubber film, soft rubber film like this. In first one, this side. When given a excess pressure, we know that pressure inside water is increasing. Therefore, this rubber film should be like this. For the second object, same method. The position is different. It is the only one difference between 2 objects. Then in A and B, total volume of the object is decreasing. Therefore, upthrust is decreasing. Upthrust decreasing, it means there is a resultant force in downward direction. We know that when considering equilibrium, there are same forces in upward and downward direction. but volume decreasing. Volume is decreasing, therefore upthrust decreasing. When upthrust decreasing, the downward equivalent force, resultant force is increasing. Therefore, in first and second situations, the object will move downward. The object will move downward. But in third situation, there is no rubber film. Therefore, the object should be at rest, remains stationary, because of there is no any volume change for the object C. Then answer should be 4 for the question number 10.